Okay. A slight departure from the usual. As mentioned last time, no more streaming in the sense of we're doing live lessons. From now on, at least for the foreseeable future, it's just gonna be some random programming. Trying to demonstrate a few of the things I've taught you. Mostly it's gonna be embarrassing myself, but that's fine. That's what streaming is for, right? And the current project I want to work on is a sort of AI for checkers. When I say AI, I don't mean the AI you hear about currently with neural networks and all that. I'm talking about just the computer enemy inside good old-fashioned classic game, which sometimes is purely algorithmic, sometimes pure random. Maybe there's some heuristics in there. The one I'm trying to do is effectively a min-max, which is why I'm picking checkers, since it's relatively simple. Though I predict I'm gonna have to do a lot of optimization for this, and we're gonna have to limit it to very small field. So some special routes are gonna be necessary. In terms of rules, I tried to look up the specific rules for checkers, since I haven't actually played in decades, I say. And apparently there are different rule sets for checkers. So I'm just gonna go with the basic. We have two different colors for two sides, and by default we can only move our pieces one by one. One player moves a piece and the other player moves a piece back and forth. Our pieces move on a grid and they can only move diagonally and only forward. If a piece reaches the other end of the board, it's getting promoted, and from then on it can also move backwards diagonally. And when you diagonally jump over an enemy's piece, that piece becomes captured, or you remove it from the game. But also if you have a situation where you can jump over an enemy, you have to do so. Of course, if you have several options to jump over an enemy, which could happen, then you still have to choose one. So it's not automatically happening then. Also, if after you've made the jump, you have another chance to jump over an enemy, you have to do it again. So kind of setting up a chain reaction. Unless you're hitting the end of the board, in which case if you promote the piece and therefore suddenly gain the ability to jump back and possibly capture an enemy piece, you cannot do that. And that's the basic rules I'm gonna go with. The board size, I'm not sure yet. We're probably gonna start with a simple 2x2 board, just to test the system. Slowly moving up. Of course, 2x2 board means you can't really do anything, so we're gonna have to test the rules, and we have to implement some kind of system to check if a move is possible and then end the game. Actually, what are the rules? The first player that cannot make any more moves loses, right? So if I cannot make any more moves, either because I don't have any more pieces or just I have no option to move a piece, then I lose. So on a 2x2 grid, basically the player that starts loses. Cool. Alright, onto the actual implementation. The first thing I'm gonna have to decide on is the game state. The way I imagine it, we have state-based system. We have one state that describes the entire game, which is just the board we are on. So let me just... let's make some drawings here. And so let's see. We have some board and... oh. I'm good at drawing. Luckily, the system actually helps me a bit by making these lines a bit straighter than they should be otherwise. So 2 different colorings for the tiles, and only half of them are actually going to be used. We have to make sure that it's an even number of tiles. Actually, we don't have to. It's just kind of a waste if we have some extra space in here, I guess. But doesn't... I mean, as long as both sides start with the same board pattern. Well, whatever. So we're gonna have the board and then some pieces. Actually, for a small one like this, let's just assume we're just gonna have 2 pieces. That's another rule we would have to decide on. And then to go from that state, we have to make a move. And once this move is applied, we're gonna have a new state. And this didn't recognize as a rectangle. Great! The system can only help me if it recognizes what shape I'm drawing, at least. Ah, that's better. Okay, let me just draw this out once, somewhat properly, and then I'm not gonna bother drawing all the different states. That's just way too much. This one actually looks somewhat good. So different board pieces, and usually the rules I saw was the darker pieces start moving. So let's say I'm just gonna make a move here for that piece, and those 2 stay the same. So the darker piece makes a move, and then the other player's turn happens and we make another move. And so this is the different states. State, move, state, move, and so on. So I thought a bit about the state, specifically how I want to store the state, since if I see 2 options. One is I store the board. Essentially I store a piece of data for every single coordinate on my board, for every single square. And each square has a couple of different options for what piece is currently occupying the board. So we have 2 players, so 2 different colors from the start. Then each token can be promoted. That means we have 4 different pieces, so to speak. Each color has 2 different token types, so 2 for each side, 4 in total. Plus we have the option of a tile being empty. That means 5 different possible states the specific tile can be in, and that for every single tile on the board. Now of course we can halve that. When we store the data, we just have to store the dark rectangles, because the white ones are never used, so it saves a bit of memory. But in the end we still store 5 different states for each tile. The advantage would be that it's very easy to look up the state for a specific tile, for example when checking the possible movements. I want to move my piece from here to here. I can just look up what's on this tile very quickly, very easily. The downside is that all of these pieces are just going to be empty and we don't need them, and we store all that extra data. And if the board gets larger, that problem becomes worse. Even if we start with a lot of pieces in the beginning, they will get less and less over time. So as the game goes on, the board will get emptier and emptier, and we waste more and more space that we just use to store the information nothing is here. Well, that's the downside. We waste a lot of space, but it's very quickly to check things on the board. The other option is we store based on the tokens. we store, let's say, a list of just each single piece each player owns, maybe all of them in one little list. And each token stores information about what type of token it is, so which player do I belong to, am I promoted or not, and which coordinate on the board am I. The advantage would be that I need a lot less space, since I only need to store the tokens I actually have in the game. So as the game goes on, the list gets smaller and smaller, and I need less and less space. Also, I have very convenient lists to just go through each piece to check the different options I have for moves. So that's another convenient coincidence. But looking up specific positions becomes harder, because to determine if a specific position is occupied, I need to go, well, not through the entire list, but let's keep it simple. In a straightforward implementation, I'd have to go through each single item in my list to figure out if that item is at a specific position. And if it is at that position, then I can make my decision, is that an occupied space? What are my possible move sets I can make now? Which becomes only increasingly problematic when I find an enemy token, for example, and then I have to move or make a decision, hey, are any of the adjacent tiles empty or not? So I might have to make the check twice. Well, okay, I say exponentially worse, but actually that's it, right? I mean, if I take one move for just one jump, if it's a chain jump, even if it's forced, I can treat that as a new move, just with the exception that the next person in turn is the same person that made the move in the first place. But no, wait, there was a rule that if I move my piece and I now am in a situation where I have to make a decision which of my pieces has to capture one of the enemy's pieces, I have to select the one that I just moved. So if I treat this as a completely second move, like if I go from, say I'm here, and there's one here, and maybe another one there. So I have to 1, and then 2. Go to this field, and then go to that field. Wait. Drew this wrong. Let me try to draw this a bit nicer. So let's try this again. So we have one over here and one over there. So it's these two at least. And I have to move to that one. And then maybe there's another one over here and an empty field over there. So I have to go through, make the first move here and then the second move here. 2 moves. I can treat this as 2 moves. But I think in that situation I am forced to make a move with this token specifically and not any other token. So it's not a completely free move. That means my moves have an additional rule set of which tokens am I allowed to use. So I'd have to somehow keep the information that this token was just moved and capture the piece. That makes things a bit complicated, so maybe instead of deciding this as one... Like, in my head I'm trying to figure out the architecture for everything, and... Oh, that's a good sign. Cool, the screen share just broke, that's good, that's excellent. Let me try to establish that again. There we go. So, again, I'm trying to figure out the architecture to see how I arrange my data, like the data structures I want to use and how I align them. So ideally I have each move of a piece as a move in the term of this is based on the rules one single action I can take to change the state of my board. But because of this special rule with the subsequent captures, I would have to keep additional information about, okay, who moved last, which makes sense, or who moves next, but I also have to keep the information, hey, this piece was moved. So if you're now in a state where you have multiple captures, this one gets priority, has to be moved first. Does that make sense? Actually, that's not too bad, right? This rule only applies if there is a follow-up capture possible. If I have other captures that are now possible, maybe because this token is now free, another token can jump. Like if there's maybe another one here, and I have one down here. Like this would not be possible for now, but once this token captured this one in the middle, when it's gone, then this token can actually jump over here. So after this first move, I have two possible captures, and as long as I keep the information that this one just made a capture, I can figure out that this one has to go to this top spot as priority. So I have three sets of priorities, I guess. One is I have the lowest level is just general movement for every token, like every move that is possible directly. Then level above that, priority 2, would be all the moves that capture the enemy token. And above that would be top priority, that's the move for capture from a token that just did a capture. So I need to either store the coordinate that was involved in the last capture or reference to the piece that did the capture, depending on which architecture I use. But then I can just keep the normal logic with each single movement, even within a chain, is one move that changes the state. Okay. Going back to the state, which do I pick? What's gonna bother me more? Actually, how would I store them? If I go just for pieces, each piece has 4 different states, 2 colors and 2 states per color, so 4 different states in total. Normal, promoted, in 2 different colors. That means I need 2 bits to cover exactly 4 states. No losses to exactly 2 bits. And then I need to store the coordinate on my field. Again, this simple 4x4 grid, I have exactly 8 different possible coordinates where a piece might be stored. How big was the... I think the standard one was 8x8, right? Eight by 8 grid for the regular one would mean 64.5, 32 different positions, 32 different numbers, so I would be perfectly fine with just 5 bits. Plus 2 different bits for the states, then I could go up to No, that doesn't make... Okay, let's say if I take 1 byte to just store the information for one single token. Means I have 6 bits. That means I have 64 possible positions I could encode if I just use 1 byte fully. So a total board of 128 pieces. Tiles, if we include the white ones. That should be enough, right? I mean, if I go for 10 by 10, that's still only 100 tiles. Only 50 for each tile that matters. That's still below our 64 we have, so... Like even 11 by 11 would be okay. Only 12 by 12 is where we... Yeah, we can go up to 11 by 11. If we make it square-shaped, I mean, we can elongate, for example, or just make it wider. So in theory, we could just say we set the limit to 1 byte for encoding 1 token and make sure that the game board cannot exceed that limit of 64 relevant tiles. And that means we can have just a byte array, for example, or byte list, byte array. We have a fixed number of tokens in the beginning that cannot be exceeded ever. So if we just start with a byte array and every time a token is captured, we just move the other pieces that follow down in that array. I mean, if we keep that in one right now, should I? No, I want to do the min-max, so I should have different states at the same time, so I would need to create a new array, but that's still fine. But that means I have a fixed array with all the tokens in there, just purely bytes. And that array would be, let's say, with a big game. Let's say I make the 10 by 10 with, what was that, 4 rows? Was it 4 rows? 20 pieces on each side, 40 pieces. That's 40 bytes per state. Plus an additional byte to store the information about which tile moved last and who gets to make the next turn. $41 bytes in total for one state. That's not bad. That's actually quite good. I'm worried about the size of the tree that we would generate for a normal game, because that could go... I mean, initially it shouldn't go too big, but once we have promotions happening, it can go really wild. I mean, there is some point where we will just get duplicates, where the moves can cause a cycle to happen, right? If there's no promotion, there's definitive end to the possible moves. So all our leaves will be within reach, just a couple of moves across the board. With promotions, anything can change, anything can happen. So we have to make some check for cycles as well. Ooh. Well, not just cycles. I shouldn't go for a tree then, it's too much. Making a hash seems reasonable though. 41 bytes. And that's the smallest one. If I make the full state for the entire game, for the entire board, I would have to store 5 states per position. And to make use of the whole speed up, each position needs to be indexable somehow. Just to speed up the lookup. And that means I mean directly it would be 5 different states, meaning 3-bit, which is quite wasteful. Of the 8 possible states we can represent with 3-bit, we're only using 5. So only 5/8 in terms of space efficiency. And then we could make one large array that stores these 5 bits for every single location. But that's also again wasteful. Even if we limit it to just the visible ones. Let's see. With the big ones we had 41 bytes. How much do we get now? With the big one, the relevant ones 50. And we probably, in a simple case, still have to sacrifice an entire byte for each position, even though only 3 of that are used. That means we had 50 bytes. If we squish everything together, can simplify that. We only had 150 bits. Wait, that doesn't seem right. Something isn't right. Wait, with the tokens I had possibly in the start of the game 40 tokens on a 10 by 10. Oh, that was my mistake. No, the 10 by 10, 4 rows. No, that was right. Of that 10 by 10, we have 5 black and 5 white tiles. So only half of them are used. That means 5 occupied tiles per row. And if we have the first 4 rows occupied on each side for each color, we have 20 tokens on each side, 40 in total. And each token has 1 byte, 40 bytes, plus 1 additional byte to store the overhead for whose turn it is and which position was the last capture. Or which tile did the last capture. Actually, that too can be reduced to just the index in our array. Plus some neutral value to indicate that there was no last capture. Makes it even simpler. Still using 1 byte though. So let's say 41 bytes. So 41 for 40 plus 1 for token list. You probably can't read it, but I can, so that's fair. If no one can read it, then everyone can't. And if we make a full state that was for the 10 by 10, that's actually just 5 by 5. No, wait, 10 by 10 means screen shares. Why is screen share always happening? What is going on? I'm not sure why screen share is constantly breaking. So we have on the 10 by 10 grid 10 rows where each second column matters. So 5 columns per row matter times 10, 50 columns. Yeah, 10 by 10 divided by half, 50 tiles that matter. So we have 50 positions we have to store data for. If that might be the issue. So with the worst case for the token list, that is maximum of 41, and it will go lower as the game progresses. So the data we actually have to store will be less and less and less. That's important. Makes also the cycle detection a lot easier, I guess. When there's only 2 pieces moving around, like maybe 2 promoted pieces, then it's just gonna be 2 bytes, well, 3 bytes that are gonna move around. That's less than an integer. That's perfectly fine. Tokens, that's a maximum, and for we have 50 states or 50 possible tiles. Each one has 3 bits. And we have to again store 1 piece of information, which tile was involved last. Let's use another tile because we can use the index, that's fine. Let's use another byte. That means we have 50. So in the simple case, we have 50 plus 1 for tiles. Or we have, if we simplify it a bit, 150 bit plus 8. It's if we squeeze all the bits together into one large byte array and we do just some math to figure out which exact grouping of bits matches a specific tile. That means the access time gets a bit slower because we have to do calculations. 150 bits. That is a pretty good result. I mean, that's less than 20 bytes. What is it exactly? Oh, no idea. Like 60 would be 20. 19 bytes. Well, we have to do 19 bytes for that then. To get to 152. So that would be, if we make this with a bit of extra calculations while looking it up, we can get it down to 20 or 19 bytes. But this would be the case for every single state. So we have either 41 bytes to start with, getting less and less and less over time, or we have a constant of 51, which, yeah, okay, let's not make that comparison, but if we optimize it, we can go down to 20 bytes. But constant. Oh, let's try to figure out in our head if this is worth it. The game progresses. I mean, to getting down to 19 plus 1, well, yeah, that means exactly 19 tokens if we go for the token list, which is half the pieces. The thing is, those big numbers, the 40 plus 1, that's something we would need in the beginning when there isn't much happening in any way. And then as the game gets as the game progresses and we have less and less tiles, we have the extra promotions happening and the different options for each state to switch get a lot bigger, but at that time we start to gain advantage on the memory. We could go the extra round and mix both systems and just pick and choose. If it's just pick the smaller one each time, right? If we have some conversion method, we can either store it as a state purely based on tokens, or later when the game is down to half its tokens, we lose a lot of pieces, and up to then we can use it purely state based, purely tile based. Maybe. If we just make the state some kind of interface and make some generic methods for accessing information about them, that's not terribly efficient probably in the long term. But it would allow us to make the most of our memory. And see, how much extra effort would it be to have it just stored as bits? If that's too much extra processing time, then it's not worth it. And right now I'm not sure what's the bigger bottleneck, the memory or the processor. Honestly, I'm tempted to think that the processor might be the bigger issue. But the memory is actually not that big overall. How do you calculate the possible states of a checkers game? That's a tricky one. Okay, let's see. If we make this efficient in one complete list of bytes inside an array, and we have to figure out each tuple of bits, we have to get the index, which tile we want. Then basically get an index inside the complete bit array. We try to look at it that way, which would be the same as for looking up with the standard system for just the index for the byte array. And then we have to do some additional math to figure out which byte that is. So we would have to divide that by A to figure out which index in the total byte array that we use as a storage container. So if it's so if we treat like that, 1, 2, 3, 4, 1, 2, 3, 4, that's 1 byte, 4, that's 1 byte, that's 1 byte, and that's another byte. So this would be a tuple, this would be tuple, this one would be 1, this one, and this one. Wait, I made a mistake. Why did I make a line in there? Yeah, this was already correct. My mistake. So that's one, that's one, that's one, that's one, that's one. So just lines up neatly like this. So to get the position for each sub-index, basically, we'd have to make the simple calculation of which column, which row. And let's say we make then column plus row times column count, whatever. Get the index for each of these numbers. Or get these numbers, these sub-indices. Then we would have to it's a lot of math. Is that Well, I'm saying it's a lot of math, but it's a lot more math than just looking it up directly. But that's taking more than twice the memory. Is that worth it? We still have to do the math for figuring out which byte array itself. Oh wait, actually if we do it this way, the math gets actually more interesting because of boundaries like this one. If I just divide by 3 and get the byte array, I have to then split it up into the specific bits I'm interested per byte. But if it's going cross borders, which is gonna happen 2/3 of the time, then I'll have to do the same with the following one. I have to check the boundaries are matched properly. Potentially have a branch there to determine if I actually need the next one over. Unless can I do that completely branchless? I think that's one of the... branches doesn't render here, right? What do I do with that state information? Evaluate if I can do something, so there's gonna be a branch anyway. And this is direct lookup, so branches doesn't matter. Yeah, that's fine. But still have to do the bit shift for each part and then join them together. That's a lot of extra work to get a throughput out of this. A throughput. There must be a term for this. 4 bits is a nibble. Is there a fancy name for 3 bits? Nah, well. Just gonna call it a throuple from now on. I'm tempted to use the token list. Thing is, the lookup is gonna be annoying. Because now the lookup is, again... Okay, when do I need to actually check the data? Maybe look at it that way. What's more likely? This down here would be the procedure I have to do every single time I do full... check... No, that's what I have to do whenever I need to check a specific position. And... to get that position... I have to reference specific coordinates on the field for each single tile. Some coordinates are even checked multiple times. If I have 2 different, like for this example top left here, these 2 tokens would both check this tile. Unless I have some optimization that can mark this down and notify all the neighboring tokens. I'm wondering, can I make this a bit smarter maybe? What if my token list is already so big? Okay, if I want to check for this token, which fields are possible, I would have to first figure out where its current coordinates are, easy. You have to figure out the boundaries of the board itself, which is also predefined, easy. And then of the possible coordinates, which can only be this one, I have to check the state of this tile. Is there any token here? For the direct lookup, I would then have to figure out the index of the byte, and then or bytes plural, and then check the specific bits in there. I have to evaluate the bits. First I have to figure out if the tile is occupied. If not, then I could just jump over. If it's occupied and it's my own token, then I can do nothing. If it's occupied by an enemy, I'll then have to figure out the next tile in that direction, if there's one, and have to make a second lookup for that. There must be a smarter way to do this. What if, instead of putting the throuple in one byte array, I make 3 byte arrays? And each one contains only 1 bit of the throuple. So every time I need to make a lookup, I need to make the lookup for 1 bit, but it happens in 3 different byte arrays. But I only have to make the calculation once, because the position will be the same in all 3. So if I do it that way, that would be first one, second one, and third one. And if I treat them as independent, I then have 0, 1, 2, 3, 4, 5, 6, 7. No, wait, I wrote this down the wrong way. This is just the arrays as they are. That's not what I meant. The corresponding values would be 0, 1, 1. The second one had 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1. That's quite common now. 1, 1, 0. So apparently I already make a couple of mistakes. I mean, I just threw down some random numbers, of course, they don't make sense, but since... No, wait, they do make sense. This is state-based, this is not tokenless. Okay, take everything back, that's fine. Can I make some more use of this? Could I take advantage of the extra space I'm using? I mean, right now, this would be a very simple lookup now. I just have to make the direct calculation for which index internally it is, which is just 1 addition, 1 multiplication, done. Or first a multiplication, then addition, I'm done. I have the perfect index. And then I have to combine the bits from 3 different arrays, byte arrays, to get a specific bit in each one. So basically I have to have a bit array. Wait, there was a bit array class. How efficient is that? I have to check up how that's implemented internally. If it's efficient, I'm just using that directly. I only need a very, very basic implementation, so maybe I'm just gonna do my own then. Because I really just need a very simple lookup for that, simplify that a bit. But yeah, if I do that, then I get the 3 different bits that describe my state. Can I make this... Wait, I think I can do a couple of things even simpler than that. I have 5 different states that I'm interested in right now. But if I arrange the bits correctly, then this could... Okay, so if I'm leaning towards the purely board-based system now. The full 20 bytes for everything. Because for the token list, I need less space, but calculating if a space is occupied is gonna basically take me the entire list to check. So I can simplify things. If I sort the tokens, if I have them, let's say the first 6 bits for coordinate, plus 2 bits state, eight bits, and I put them in the higher order bits, the first 6 bits, and these 2 for the state are the least significant ones. Then I can just sort these bytes by size, and then can be, for example, coordinate 0, 1, 2, 3, 4, 5, 6, 7, and so on. Or well, actually, only the important one are 0, 1, 2, 3, 4, 5, 6, 7. So, like that. And with that, I can simplify my search for a specific condition by just, well, basically doing a binary search. Pick one in the middle of my token list, and if it's bigger than my coordinate, I'm moving further up. If it's less than, I'm moving further to the right or left, depending on how I sort the list. And actually, knowing how far I'm off, I might be able to make some distinction. So if I check this field, for example, and I know this is not far enough, my token is further, the position I'm interested in might be this one down here, or maybe this one down here. And binary search, I would just go for the middle, maybe round it down, so I would check here. But because this is row-based, I can make maybe a check. I think this is the field I'm testing now. I know the field I'm interested in would be in the right part of the right half of the entire field. And so maybe I can, instead of going for a standard binary search, influence it to not split the results exactly in the middle, but move the next goalpost more in one direction, depending on how many tokens are left. So I could make a binary search that's potentially even a bit faster than standard binary search, because I have some additional information that can improve the accuracy of my guesses, so to speak. But that means I still have a binary search with a lot of lookup and branching to find out if a specific position is occupied, and I have to do that again a few times, potentially for different tokens. Because the same field might be tested for, like in this case, this token. Well, I mean, in the same turn? Yeah, no, it might still be possible for the same turn. The same tile might still be checked by different tiles, even from the same color, so... Alternatively, we could also, of course, make it the other way around. Instead of having our tiles check, or our tokens check if there is a move possible, every time you make a move, you update only the tiles that have changed. So if I move this token here from tile down bottom left to this tile here, I make an update to all adjacent tiles down here, because suddenly there's empty space. And I have to update all neighboring adjacent tiles from here because there's no more space. Plus, this might be a chance for some other tiles to make a jump, so I have to update the direct adjacent neighbors and the ones adjacent to that as well. So if I have 3 and so like in my case down here, once I make the jump to here, I might need to update that tile as well. Am I gaining anything? This would be mostly useful for the purely token list. I'm leaning towards the state. I like this system. So if I make this clever, I can use the index, which is very simple and easy to calculate, and just question the first byte array, or bit array specifically. And this might be, let's say, a 1 for the tile is occupied and a 0 for it's not occupied. And if it's a 1, the next two arrays will give me an indication of by what tile. And I can make it again structured in the way that I then look up the next index or the next bit array value, which could be the color. So I'm probably only interested in, is it an enemy or not whether or not they're promoted. So I'll need to check up the first 2 bit arrays at most. And I might need the third one just in case I want to check if my move is possible from a certain position to another position. So I need to know if the starting position is actually a valid piece for that move. Just for validation, I might need the third bit. For the most part, I'm just going to need the first and second one. And since we're expecting the field to get empty over time, the first one is just going to be 0 a lot of the time, in which case I don't even need to look up the other twos. So it saves me a lot of time there. Very quick, fast lookup. And very easy structure. Though it does take still 20 bytes per state. And in the example of 10 by 10. I think that's good though. Plus with this system, I'm not limited to the size as much as I'm here, because as my field increases in size, I need more extra bits for storing the extra information for the possible coordinates. So once I go 12 by 12, for example, if I make a square grid, this cannot store the information anymore. I need 7 bits for the coordinates. That means I need 9 bits in total. So I have again a situation of either I waste 2 bytes or I have this ugly situation with multiple byte arrays kind of mixing and matching across boundaries between, making calculations a bit more annoying to deal with. So I'm secure for that. Yeah, no, I think I'm gonna go for the purely state-based, the tile-based system. Let's see. We have tiles. For each tile, I have bit position in 3 different arrays. Bit arrays. I only need those 3 bit arrays forever, because there's only gonna be 4 different states a token can have. The 5th state is just for empty tiles. And that means I also have 3 additional values I could store to represent something. So in case the first bit is 0, and it indicates that this tile is empty, but then I have 4 different ways the field could be empty. So I could actually still do the whole reverse lookup. So I'm not sure yet what I would use that information for. Maybe later for indicating that there's capture possible here. Anyway, the extra byte would be just for the, so I have the 19-bit for the 10 by 10 example, plus the extra byte to just store 1 bit for whose turn it is, and that leaves me still with 7-bit to encode the position that made the last capture, or the position of the token that made the last capture, with one state being for, let's go for the 0, representing nothing. Maybe not 0, that might be inconvenient. But yeah, 7 bits. That would refer to one of the possible positions in our bit array. How many bits do we need for the 10 by 10 grid? I'm going for 19 bytes that need to encode everything. Well, 150 bits. Let's go just for the bits directly. Let's ignore those. 150 bits. Seven bits don't cover it anymore. Dang it. Oh wait, no. It totally does. Those 150 bits are for the old system I had in mind for everything is in 1 byte array. I have now everything split up in 3, so it's only a third of this. That means 50 plus 50 plus 50. Plus 8. And yeah, 50 is totally within 7 bits. I mean, 7 bits I get 128. So 128 minus 1, so 127 tiles are possible. I could go for 127 tiles. And with that, cover everything in 1 byte for the meta information. That's good. Okay, let's just try to implement this. Just rough outline of the different data structures I need right now. And just write something out. I'm not gonna bother with extra files for now. It's just having a rough idea of what things gonna look like. And I'm gonna make a record for this. The data is in a bit array for each state. And I want states to be immutable. Yeah, let's make a record. We can change things later if they become more efficient a different way. Let's use a record, public record, state. And we're gonna have, let's go for a mutable array. No wait, not immutable array. I was going for 3 immutable arrays for our bits, but let's go for bit array for now. Bit array. Hey, good names for the 3. Bit array. Occupied, let's go for the first one. It's occupied. The next one is bit array color, and the last bit basically for each position would be bit array for promoted. And then lastly, let's smash them together. Oh. I could make my life a bit easier if I just split this out into a bool, but I do want the efficiency, I guess. So maybe... No, this is not quite what I want. Is it? Let's not make those public. No, I wanted to keep things easy. For now, let's just go for the standard one. I'm gonna worry about accessors later. I don't think I want to have everything laid out like this. Byte. Metadata. Metadata, like that. That's gonna be the state. For up to 127 occupied tiles, so 254 tiles in total. Like that. And we should also create a move. Record move. Now the moves are... Whoop. Sorry, that must have been a bit loud, I guess. So, to go from one state to another, it's always about moving one tile to another position. And technically that's only one of 4 possible positions. For a simple token, that's only 2 possible positions in the most extreme cases, and for a promoted one it's 4 in the most extreme. So I could reduce a move to which token, so just coordinates for the specific token that I do change, and 2 bits to determine a direction. If I really want to reduce the footprint of that move. But that's unnecessary, I think. For now at least. We can still do that later on. But let's for now just focus on preserving processing rather than memory. That would mean I have before and after for position. Let's assume the move itself was tested beforehand. Basically, we evaluate the field, determine the possible moves, and one is chosen, and this move includes the total evaluation for is this possible, all the evaluation needed for what can we do, what happens inside. Should the move itself contain the information that another address is removed? No, it doesn't need to, right? If the move says only move by 1 field, then normal move, nothing happens. If it says move by 2 fields, so jump over, basically, if it's a larger distance, then it's a capturing move. So we could also include that as an extra bit, because we know that beforehand as part of the evaluation for what moves are possible. So let's see, we have 2 addresses, or 2 locations, 2 coordinates. Each coordinate for us for now is possible within 7 bits. In our case, we even have definitive locations we move to. So technically we have 128 possible states, but yeah, 107 bits for both. Our state limits us to 7 bits, at least for now. So we can also accept move to just be 7 bits per coordinate, yeah. So 14 bits in total. And that means we have still 2 bits left over which we can use to indicate if there's a capturing move. That would be 1 bit, and that means we still have 1 bit more we could use to flag something. But I'm not sure what. Well, that's good to know. So 2 bytes for move. Let's say byte move. Well, let's say move from byte 2. Oh. And then we would have something in a state. To simplify things a bit, that would be public state fly. That would receive a move. And then return a new move or a new state. And we would also need to have something like renewable move get possible moves. Like, I would still have to write the code out, of course, but this is just organizing my thoughts basically in code. Feeling out a structure I want to go for. Now the next interesting thing, rules. Because I'm so far working with a very strict rule set, but do I want to make the rules a bit more lenient? Do I want to make them configurable? It's probably cool if I can get it to adapt to different situations, but I'm not sure if I want to. Let's say what rules would be, I mean, the size of the board is already adjustable, doesn't really matter. I mean, I'm limiting myself to 254 tiles, or 127 relevant tiles so far, but that is just a single value that I can easily adjust. I could just make another type with as many bytes or bits as I want that stores the entire position. So I have an extra type for address, that's possible. And the number of tokens is also not relevant because I have the entire board. The number of tokens doesn't change anything. As long as the tokens fit on the board, I can have as many as I want, or as little as I want. That's all just the starting condition. I guess the only rules are for the extra rule, maybe for do I have to capture next token? But I think that's easy enough to set up later. Like if I make my check for possible moves, I just start with, hey, which moves can this token make? And right now I would have a system where I get the different moves and then have them spread in 3 different priority lists or layers. And once I hit a higher layer, I remove everything that was before and just assume this is the new threshold. I could change it later then to not do that and keep all the possible moves, I guess. Yeah, I don't see really a value right now in having custom rule sets, making everything way more complicated than it needs to be. But for this, what I imagine would be something like last move was a capture, which would be something like metadata. Metadata and 1. Oh, not that one. And 1 equals 1. Oh, that way. That way. So it's bit 1 set. That could be the last move was capture. Ah, no, wait, that's not what I want. Last move was capture. This would be... initial state should be all zeros, then... Player 2's turn. So the last bit means the second player's turn. The second player would be the second person to make a move. We start out with metadata all at 0, so this would be false. It's player's 1 turn, or player 1's turn, that way. And public bool last turn was capture, just for a quick fix. Good metadata shifted over by 1. It's greater than 0. And we can have byte last capture. Last capture was like that. Validating the metadata would be then just least significant bit for which turn it is right now. So I check this to determine which player has to make this turn. Starting off with player 1. And the next 7 bits up determine which piece made the last capture, or at which coordinate you can find the last piece to make his capture. Now, at which coordinate to find the piece that made the capture last turn, so like that. And that would be that. I should subtract 1. Like that. That's better. So 0, the default would be there was no capture, so this would be nonsense. I should probably make some clever logic around this. Instead of having this as 2 properties, that's just waiting resources. I have to rewrite this in the actual logic later on, depending on how I use it. But yeah, the next 7 bits up would determine the position of the piece that made the capture last turn, and if there was no capture last turn, it would be just 0, which is also the default value everything starts with. And yeah, to prepare the board, I would have to do something like public static state create new board and width and height and tokens, and based on that then create the bit arrays based on width and height, and the number of tokens is to determine how many tokens each player starts with. So I can change most of the board to just, well, actually not most of the board, I can change the board positions to either be unoccupied, just 0, or occupied by default token of the respective color on both sides. I'm gonna go with width is the line between the two players and height would be the distance between two players. So basically, if you're looking at the board, you're looking at the board to play. Players in front of you, so width would be the full breadth of the board. You can play to the left and right. And height would be how far away is your enemy, opponent. Opponent is more friendly, let's go with that. I think that's what I'm gonna go with. So this took me a while, but that's the kind of stuff I go into when I try to design a new program. A lot of theory crafting and a lot of, okay, how do I even roughly structure things? What are my basic data structures I'm gonna work with? What is the data I need to store? Make some guesses, maybe write out some data for specific use cases, and then try to make an educated guess about what's more efficient, what's gonna be more easy to work with. That's what I decided now. This is probably gonna take a lot more space, a lot more space in the long term than just a token list. But I'm prioritizing now processing speed and ease for programming. And depending on how I write this should be actually not too hard to switch out. So that's what I'm gonna try to do later on. Make it so that the actual implementation for this state can be changed and the rest of the logic is unaffected by that. That's gonna be one of the priorities when programming it. Also, now that I've written this down in program roughly, I should probably write this down for myself. If you're working on a large project, it helps to write down your axioms, basically your basic premises for how you want to write a program. If not for yourself in the future, then maybe for your teammates, and maybe a little documentation to why did you get to that conclusion. I'm not gonna do that because I'm too lazy for that. Also, everything is recorded right now, so if I'm not too sure, I can just look up the VOD. And so can you. And honestly, I'm gonna stop for today, because I got some other stuff to do. I'm not one for long streams anyway. Not like we did much, I know, it seems like that, but this was important first step for the program. Next time we're gonna have to actually put this into code that works. Look forward to that. Until then, have a lovely Sunday. Bye bye.